Hello, class 10th physics magnetic effect of current. Today's topic magnetic field due to current carrying coil or current carrying loop. Well, if we want to draw a diagram of magnetic field line, then for both it is same. However, loop is just a single turn of a wire, whereas coil is a number of turns. But there is a concept of solenoid also. Solenoid also exists. And now, what is the difference between coil and solenoid? Well, for that, watch this.
It. So this is a coil and this is a solenoid. The difference between a coil and a solenoid is that a coil has lesser length and greater diameter, whereas a solenoid has larger length and lesser diameter.
So right now I'm drawing the magnetic field line for this arrangement, and we will apply Maxwell right hand thumb rule for this. Current is going up, we'll grip it like this, and on the other side current is going down and we will grip it like this. So here, inward from this side, outward from other side, and for here, inward from this side, outward from other side. It means from both the for both the element, magnetic field line is going inward and from here outward. Try to do it yourself, so you will easily come to know what I am trying to explain here. So this will be the shape of magnetic field lines. Here also. Oh, I'm not completing these, but actually these are complete circles. Okay, there will be some bigger arcs, bigger magnetic field lines, even bigger. And remember, that's very important. There will be a magnetic field line passing just through its center, which is perpendicular to the plane of the coil. This is quite interesting and quite important, and as far as exams are concerned. See, all other field lines are not perpendicular to the plane of the coil or loop, but the magnetic field which is passing through the center is perpendicular to the, or in more scientific manner, normal to the plane of the coil. So now what are the properties of magnetic field lines due to loop? Okay, so first thing, magnetic field is perpendicular to the plane of loop or coil, whatever is given at the center.
So right now this compass needle is showing the Earth's magnetic field, and when I will switch on this, it will show the magnetic field of a coil. See, the magnetic needle is deflecting. It is showing the straight, means it is the magnetic field of the coil.
Second thing, magnetic field is strongest at the center and decreases as we move away from the coil. I would not say that directly or inversely, it is a bit complicated. So just keep this thing in your mind. Magnetic field is strongest at the center, and if we move away, it decreases. Next, third, magnetic field. In previous videos, I have introduced this for magnetic field. Okay, magnetic field, that is B, is directly proportional to current. Means if we increase current, then magnetic field will also increase. I'm not writing it in my statement, but you need to write it because maybe you will get confused what is happening here. It is all about loop and coil also, but one thing, for specifically for coil, B due to coil is directly proportional to N, that is number of turns. Means if there are more number of turns, then greater will be the magnetic field due to that coil. See, this question can be asked in a different way. So, sometime there is a diagram and they can ask using this diagram. There's a cardboard and a coil which is half visible on the upper side. It is something like this. And here we have connected it to some circuit. So I think both are looking alike. And see, this is current. So sometimes such type of diagram they can give. In fact, they can give entire diagram and you have to find out what is it. And sometimes you have to write an activity how to draw magnetic field line due to this arrangement. So simply in all the cases, all those cases, you have to follow that experiment in which we use a compass needle and just trace the path of the magnetic field line. So also here, simply it will be like this. Okay, and let us suppose it is the midpoint. So one of the magnetic field line will go straight away this way, and here also. That's all. Okay, and sometime it is also asked, and you people might think that how is it possible, from where current is going? So they have ignored that part, but okay, just they have drawn this, and now you have to draw magnetic field line due to this, and you need to just draw it like this. Keep the thing in your mind that from here magnetic field line, see, these are curling this way, and for this it will curl on other way, and there will be two field line for this end and for this end. They will overlap and they will form a straight normal to this surface. Okay, next topic, magnetic field due to a solenoid. But before that, what is solenoid? So earlier we have discussed it, like if there is a single turn. Actually this is a 2D diagram, so don't laugh at it. So this is a loop. This is a two-dimensional diagram actually. This is a loop, and if there are more number of loops, it is called coil. Now this is solenoid. Now what is the difference? In each case we have a current carrying wire, most of the time copper wire. Why copper? Because it is a good conductor, best conductor in fact. Actually best conductor is silver, but after that it comes copper, which has very low resistivity, and it comes at second place after silver. So it is most of the time they say that this loop or coil or solenoid, they are made up of copper wire, and they use a term insulated copper wire. Insulator copper wire nahi, they use the term insulated copper wire. Copper wire insulation. This is a copper wire and it is coated with a plastic covering. Or sometimes you might see copper wire having brownish coating. That is not actual color of copper, but that is an oxide layer over it. So a layer over it which makes it insulating copper wire, insulated copper wire. So like this is an insulated copper wire. See, this is copper wire and it is insulated. And this one also, this is insulated. I have scratched its end so you can identify this is its actual color and this is a coating over it. So now as we have seen in that demo video, the difference between coil and solenoid. So coil has, this is its length, this is its diameter. For coil, diameter is very greater than its length, and vice versa for solenoid. For solenoid, its length is very greater than diameter. This is the simplest difference between coil and solenoid. Other than that, mostly solenoid has a large number of turns. So now how will we draw magnetic field due to solenoid? So for that, just follow in which way I am drawing it. Current is going up, coming out, going in, 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 coming out. That's all. And due to for this diagram, you can use some dotted lines. This is solid line and then magnetic field with the dotted lines, but I'm using two different colors, so no problem with me. I'm using solid line for both the cases. So inside the solenoid there is uniform magnetic field. Now what is uniform magnetic field? Remember, uniform magnetic field is the magnetic field which has a particular direction, in which the magnetic field lines are parallel to each other and equidistant. Means if this is not a uniform magnetic field. Second thing, this is of course not a uniform magnetic field. In fact, this is not a uniform magnetic field, but this is a uniform magnetic field. Uniform magnetic field must be parallel magnetic field lines along same direction and equidistant. These are not equidistant. These are equidistant. So, and outside the solenoid, they form a closed curve, same as that of bar magnet. So, in a bar magnet, solenoid is a replacement of bar magnet. Now, properties. First thing, magnetic field is uniform inside the solenoid. Second thing, magnetic field is similar to that of magnetic field of bar magnet. Third, magnetic field increases with increase in current. If we increase the current, then magnetic field will also increase. Fourth, magnetic field increases with increase in number of turn. And fifth, magnetic field increases if an iron core or any ferromagnetic material is placed inside it. So if we place an iron rod inside this solenoid, then its magnetic field will increase. It will become stronger. I'm not drawing inside because it will be very hodgepodge there, but I'm drawing outside. And most importantly, for an infinitely long solenoid, means a very long solenoid, there is no magnetic field outside it. It means if its length is enormously large, then we will not get a sidewise magnetic field. Also, when an iron core is placed, okay, this solenoid is also called an electromagnet. This solenoid is also called an electromagnet. What is an electromagnet? So, electromagnet is a solenoid whose magnetic field can be switched on or off by switching on and off current through it. Or simply we can say electromagnet is simply a solenoid, and in a solenoid, if we switch on the current, then magnetic field develops, and if we switch it off, then magnetic field also decreases to zero. So electromagnet, in fact, electromagnets are very handy tool. If we can increase their magnetic field, we can decrease their magnetic field, we can switch them on, switch them off as our requirement. Other than permanent magnets, conventional magnets, normally used magnets which have a permanent magnetic field which cannot be switched on or switched off instantly. So we have discussed about current carrying coil, current carrying loop, current carrying solenoid. But one thing for sure, that if there is current, then it produces magnetic field. We know that if there are two magnets, then they will either repel each other or they will attract each other depending upon nature of poles. Now we know that a current carrying conductor also have a magnetic field associated with it, either a simple straight wire or a current carrying coil. So what if this wire is placed near a magnet, whether North Pole or South Pole, or this coil is placed near a magnet, external magnet, either North Pole or South Pole, then how will it behave? Will it experience some force? Yeah, of course. And if so, then in which direction? And by the way, there are few other things I want to end this video by saying. If there is a loop and current is flowing through it in a clockwise manner and in anti-clockwise manner, and if we have to decide this end is behaving like which pole, then remember alphabet S and N. So if it is clockwise, then it behaves like south pole, like here magnetic field line is going inward, and if it is anti-clockwise, then it is north pole. This is the one thing. Other thing, as I told you, like this, if this is current, then curl of the finger is magnetic field. Now as you can see, I have drawn a solenoid like this. Now current is curled this time, and this rule, Maxwell's rule, is still applicable. Now we need not to grip this wire, but if you hold this solenoid with your right hand like this, then with right hand, then the outstretched thumb will show the direction of magnetic field. So this time I'm just reversing the law. This is current, so this is magnetic field. In short, if current is straight, then magnetic field is curled, and if current is curled, then magnetic field is straight. I repeat, if current is straight, magnetic field is curled, and if current is curled, then magnetic field is straight. See you in the next video.